In this video, we will go into how the mean is defined and what that means. We're going to use this example of 5 students measuring the height of one other student with a measuring tape and producing a set of estimates that we have from a previous class. And the question is, what should we answer as being the person's height? So here we have a graphical display of measurements of this person's height. And on the horizontal axis, we have values that could be reported. And on the vertical axis, we have the number of times that each value was reported. So in this particular case, the first person reported 163.5. So we draw a line from 0 to 1 to indicate that the value 163.5 right here occurred once after the first person had measured it. After the second person, we have one occurrence of the value 162 in addition to the first one. And then 3 more people measured the height. And so we have finally 2 measures at 162. That's why this line goes all the way up to 2. So this shows us the distribution of the actual values reported as measured height for this person. And the question is, how can we derive an answer from these? So to see how we can calculate a reasonable answer, we will imagine we have that answer, and we will just draw a line to represent it, and use the symbol mu to indicate this value that we don't know yet. So let's imagine that our answer would be somewhere around here. How much do the actual observations differ from this desired answer? We can subtract this from each observation to find the distances. So these d values are the distances. d1 is the difference between the first measurement, designated x1, minus this value, which we don't know yet, but we can still write that d1 equals x1 minus mu. So the first distance equals the first measurement minus this position, whatever it turns out to be. And we can do the same for the other values that were reported. So we have 5 distances from this hypothetical line, and these are the 5 differences of the actual observations. Notice that the way that these are displayed, 2 of the measurements are to the right of this hypothetical line. So if we subtract this from that, we get a positive number. The same is true for this one. x1 minus mu will produce a positive number. This is a positive distance. And x4 minus mu, again, will be a positive distance because this is more than this. It's to the right on the axis. In contrast, x3 minus mu will produce a negative number because x3 here is less than mu, the way they are shown right now on this example. So this is to the left of that, therefore their difference will be negative. So now we can begin to think of this line as a line that is pulled by the different observations. And we want this line to just settle wherever all the different pulls balance out. We will accept this as an optimal answer from the 5 data points when we allow each data point to pull and let this line settle wherever all the pulls equal in the 2 directions. Another way to state that is that we demand the sum of all these distances to equal 0. When is the sum of all the distances going to be 0? It's going to be 0 when the positive ones pull to the right exactly as much as the negative ones pull to the left. So because these are positive and these are negative, when all the positives sum up to exactly the opposite of these negative ones, then the sum of all of them together is going to be 0. So we demand this, we set this to be the case. It's not that we know something about the distances. All we know about the distances is that they're defined by a subtraction, but we don't know mu yet. So we say we want the distances to add up to 0, and that's how we define where we want this line to be. So to proceed, all we have to do is substitute the d values from their definitions. So the first distance equals x1 minus mu, the second distance equals x2 minus mu, and of course we retain the demand that this sum has to equal 0. Now all we have to do is group together all the x's here and all the mu's. We're not changing anything, just moving them around on the same side, so that we see that there's 5 of them and 5 of them. And we can take all the mu's to the other side by changing their sign. So instead of subtracting them on the left, we add them on the right, which is exactly the same thing. And then, well, if there's 5 of them, we just write this as 5 times mu equals the sum of all these values. Just take these 5 and discard the 0, which doesn't add anything. So based on this, we can solve for mu just by taking the 5 on the other side. So if 5 times mu is equal to the sum, then mu is equal to the sum divided by 5, which is the formula for the mean that you already knew. What this means is that the mean expresses the idea that it's a balance point. It's the point where the pulls from all the available data settle and counteract each other exactly. And in mathematical terms, this is exactly the same as saying that the total distance equals 0. That is, the positive and the negative distances exactly balance out. Remember, we started by just drawing these distances and this line, but not giving them any value. The value is derived from the measurements after we demand that they all add up to 0. So this is how the mean arises. And its actual value in this case is indeed 162.3. And if you want to add up the values of these distances, now that you know this, you can subtract it from each observation to find these distances here. And if you add these two, you'll see that they exactly counteract these 3. So that is what the mean is and why it is equally affected by every observation that we have. This means that unless the observations that we have are measures of the same thing, and in fact equally good measures of the same thing, then allowing them to go into the calculation of the mean would be misleading. And this is the important assumption for calculating a meaningful mean, which also has the useful properties of minimizing errors and other ones that we'll encounter later in this course.